All right. Today we will continue with the sampling topic, and we will try to wrap it up, complete the topic. There are a few issues that are remaining that I want to talk about. The first issue that I want to indicate is regarding the visualization of aliasing for some specific types of signals. I will start by focusing to what is happening around the sampling frequency. As we know from the example that I'm showing to you, from this example, where we had a sinusoidal signal, a cosine, with a frequency of omega 0, and we know that if the sampling frequency omega s is more than twice of omega 0, then the two impulses that are generated by the cosine will be repeated at individual or isolated places. However, if the sampling frequency omega s is not greater than 2 omega 0 but less than 2 omega 0 like this, then the impulses, the two impulses, will again be repeated periodically with omega s, around omega s, but they start overlapping with one another. They start appearing inside a place which shouldn't be inside the place. But now I would like to focus a little bit what is happening here at the point of omega s over 2, okay? So I'm talking about this point where it actually corresponds to omega s over 2. Now notice that around omega s over 2 point, which is the Nyquist frequency, since omega 0 is more than that one, more than that frequency, it appears at omega 0, and a replica of it, which shouldn't be there, appears at omega s over 2 minus some place. Well, actually, it is at omega s minus omega 0, typically, but these two distances to this point and to this point, starting from omega s, are equal. So the signal is like folded around omega s over 2. One of them appears at omega 0, the other one appears as a shadow or a ghost version inside omega s over 2 at an equal distance. So when we sample with omega s and reconstruct, we reconstruct something which is like the folded version of omega 0, and that is the alias of omega 0. Although we have observed this phenomenon and we have found the analytical formulation of that new signal, the red and green signals I'm talking about here, this red signal and the green signal here, they are not at omega 0, but at the folded frequency. If omega 0 is even larger than that, then its folding will be even with smaller frequencies. So around omega s over 2, these two frequencies of omega 0 and its shadow version will be separated from one another even more. And the green and red signals will start merging to each other. This kind of a phenomenon actually happens for any kind of a band limited signal around omega s over 2. So I want to, for instance, make another example. It's blue, but yeah, no problem. Let me continue with black. In this new example, let us focus to what is happening. So I give some break here. And let us assume that this point is omega s over 2, and around omega s over 2 position, around the Nyquist frequency, let's think of a band-limited signal with the Fourier transform of this shape. Oh, actually, this is a little bit inappropriate because I would start by talking about this shape. So if around omega s over 2, we have this kind of a shape where as you see, it's to the right of omega s over 2, whereas everything should be essentially to the left of omega s over 2. So this appearance is not suitable for sampling without aliasing with omega s over 2, or sampling with omega s actually, because omega s is to the right-hand side somewhere, and it is less than omega 0, twice of omega 0, because omega 0 at this point would really correspond to this point. So omega 0 is unfortunately not to the left of omega s over 2, but it stays at the right. If you have this kind of a sampling phenomenon, then the sampled signal after reconstruction will look like the folded version of it, like this, the blue one. The blue is the alias of this. Come on, of the black signal, like this. So the example that I have shown for the cosine, where the two impulses around omega s over 2 are separating a little bit, that situation is not specific for a cosine or a sine, a pure sinusoid, but it is specific, or it can be observed for essentially all types of signals, band-limited signals like this one. And if the situation is further like this, like we have a point corresponding to omega s over 2, and the signal extends from inside omega s over 2 to outside of it, with an omega 0 corresponding to outside of omega s over 2, which is a bad thing that will correspond to aliasing, then its fold will be like this. Okay, and inside this folding, there are even further problems. At the example in the top, we have two separate aliased versions and unaliased versions after the digital or discrete time reconstruction. So what I'm saying is actually, we can write it here, the sampled signal, which is the discrete time signal, in other words, x of n, may correspond to the blue or the black signals. And you don't know which, okay? Although you know the sampling frequency, you know omega s, you cannot resolve whether it corresponds to the blue folded version or the black itself. There's no way to separate it. But if you know that there's no aliasing, then it will clearly correspond to the black signal. It will not correspond to the blue signal. That gives us the ambiguity, because in case there's an aliasing like the black version, which is not suitable for non-aliased sampling, when you make the aliasing with this specific value of omega s, it actually looks like the blue signal with a lower frequency and with some foldings in the spectral domain, so everything is being spoiled. And in the second example, the spoiling is also eminent. You cannot resolve whether it's really corresponding to, the result is corresponding to the black or the blue. And when you further make a filtering, a low pass filtering, starting from here, going inside, as you see some, I cannot see it. Oh yeah, it's here right now. You cannot depict even the tail portions. The tail portion is folded actually again. The black is folded to blue, and the tail of the blue is folded back to the tail of the black, etc. So these are things that you must always avoid in sampling. In short, you have to use either an anti-aliasing filter, which completely eliminates everything above omega s over 2 before sampling with omega s, or you must choose omega s, which must be greater than twice of omega 0, the maximum frequency that you may encounter in the signal. These are the conditions that you must have. Of course, we have also seen a situation where, as long as they don't overlap like these, you can actually not apply the regular low-pass filtering for digital to analog conversion, but you can apply a band-pass filter for the reconstruction. That is a possibility, of course. You can do that, but it would be quite specific or dedicated to your sampling system. And there's also one final remark that I would like to make. This is all for these, all the analysis that we have seen are for sampling with a uniform period, okay? The period of the impulse train or the frequency of the impulse train does not change. There is a research topic for you, according to your grade for the undergraduate level. That's not correct to mention about these, but you may be curious about it. There is also something called non-uniform sampling. So the sampling period is not staying the same, but it's changing randomly. With that kind of a thing, you can go beyond the Nyquist limits, and you can have fewer number of samples to reconstruct faithfully the analog signal. It is also known as sparse sampling because you know, the number of samples that you have will be significantly less than the number of samples when you apply uniform sampling. But what we are seeing right now is uniform sampling, and in the majority of technical engineering topics, we are applying uniform sampling for audio, for example. But if you're in the space, if you are doing something military and where the number of coefficients is too valuable, you have to focus down to that concept of sparse sampling. That is also a research topic that you may be interested to learn. We don't even cover that in the master's level. If you're doing PhD level research, that sparse sampling is an issue, for instance, for you guys. And then the next thing that I want to talk about is, it's red, let's change it to black. Discrete time sampling of continuous time signals. This is something that I have briefly mentioned in the previous lecture. It's the process of making signal processing using computers, but the eventual input and output relation would be continuous time. So we have a continuous time signal x of t, which goes into a system, and the output is y of t, which is also a continuous time signal. And in between something is happening, which is equivalent to a continuous time, let's say linear and time invariant, because those are the things that we can analyze. We know how to make the analysis. And h of t filter. So from x of t to y of t, the impulse response is h of t, or the transfer function or the frequency response is h of j omega, which is the Fourier transform of h of t. So inside this dashed box, the overall effect is h of j omega. The problem is, how can we implement this h of t or h of j omega using a computer? So since we want to use a computer here, we must have something like an analog to digital converter. Let me put it here, A to D converter. And then we have a process we can call h of n, because since it is discrete time now, the filter that we are going to apply will be a discrete time filter, h of n, whose Fourier transform is h of e to the j omega, okay, either of them. And after that, there is, sorry, a digital to analog converter back, and it provides the output to become y of t. The question here is, how can we relate this black h of n or h of e to the j omega to the blue continuous time h of t or h of j omega? How can we find the relation between those? Now, there are some limits of this thing, just like the Nyquist limit of x of t that we have, which is band limited. The corresponding effective h of t must also be band limited, or eventually, since x of t is band limited, h of t, the effective range of h of t will also be band limited. Look at this kind of an explanation. Let's assume that inside here we have x of j omega. So this is x of j omega with a maximum frequency of omega 0. Okay, band limited like this on the frequency axis. If your filter is wider spectrum than this one, like maybe from here to here, so this is h of j omega, okay? The effective h of j omega doesn't need to be up to omega 0 prime, because between omega 0 and omega 0 prime, it's actually doing nothing because there's no signal there. The signal content is unavailable over there. So why do we want to implement this particular blue h of j omega, although there is no need to have it completely between omega 0 and omega 0 prime? So we are going to crop it with this green crop and consider h of j omega only between minus omega 0 and plus omega 0. That is the place that we are going to focus to h of j omega. And we will reproduce that portion of h of j omega using h of e to the j omega, using the discrete time system. So the discrete time system will not cover these places. Let me write it. The discrete time h of n or h of e to the j omega will not be concerned with these regions. Okay, So we can assume that actually those regions do not exist. Anything beyond omega 0, the band limit of the signal, does not exist. There's no signal there, so there's no system there. There's nothing to act on the signal. So no signal, therefore no system over there. Now the example that I will show you will also illustrate how to attack this kind of a problem, how to find h of n that is partially doing this h of t. It is only partially doing h of t because it's doing h of t only up to omega 0. Let me also write it. So h of n mimics h of t only up to omega 0. Okay? From minus omega 0 to omega 0. Within those ranges, we are doing it. That's the way to approach discrete time processing of continuous time signals. The signal must be band limited because everything Nyquist, as you see. Now the example is as follows. We have, or we want to have a system which takes the derivative of the input. So x of t is the input, and y of t is essentially d by dt x of t. It's taking the derivative. It's a very small, primitive differential equation, which is just taking the derivative of the input. How can we make this derivative implementation in discrete time? And we know that in image processing, for example, if you want to find the edges, which are abrupt variations, we want to mimic this derivative operator because the derivative of an edge will be too much, too large. And when we apply a threshold to that derivative output, it will give you the locations of the edges in 2 dimensions, of course. That's for images. So in image processing, this is quite critical. And the system, let's say h continuous time of j omega, corresponding to this derivative operator, as we all know, is j omega, because x of j omega is multiplied by j omega to give y of j omega. Therefore, the frequency response is j omega. In the impulse response, it's quite difficult to obtain this from here because it's not really made for, this system is not really made for impulse responses. The impulse response is difficult because it requires the derivative of an impulse. The impulse is already an extremely sharp peak spike. If you further take the derivative of that already extremely sharp peak, you have to find a new notation for that. And the notation for that is the derivative of the impulse. So the impulse response for this system is the derivative of the impulse. The inverse Fourier transform of j omega is therefore the derivative of the impulse. Strange, but useless nonetheless, because we're not going to do it that way. We're proceeding from the Fourier domain. In Fourier domain, everything is bounded and limited. It is h of j omega is equal to j omega. Now, when we look at it, the h of j omega in magnitude like this, we will see that it's essentially these 2 straight lines, okay? 2 plus and minus 45 degrees and 135 degrees lines, because it's the magnitude of omega. The absolute value of j omega is the absolute value of omega, and the absolute value of omega is this shape. Now, what I'm going to do is, I'm going to apply a band limit to this one, because normally, of course, it's not band limited. H of j omega is extending to infinity frequencies, but I'm gonna limit it, and Let's draw it with a different color. I'm going to denote it H, H of j omega. The previous one was HC of j omega, but this one is H of j omega in magnitude. So I dropped the C because this is the band limited version of that. And it's going to be like this. Okay. From minus omega 0 to omega 0, the 45 degrees, and then abruptly they stop magically. Of course, it doesn't need to do it, it doesn't have to be like this in the continuous time. In the continuous time, it could be just the derivative operator, but since the input is bounded between omega 0 and minus omega 0, we don't really have any opportunity to apply anything beyond omega 0 from H of j omega region. So I'm assuming that this is the equivalent system. Now, this equivalent system can be converted to the discrete time system, just like by sampling as if it is a signal. Although it is a system, it's an impulse response, and the Fourier transform of the impulse response, I will assume that the impulse response is a signal, and I will sample the impulse response, which means I'm sampling H. So I'm going to do that. And I will call it H sub D of j omega first. First, it is still j omega. It's not really discrete time, but it is sampled version of it, sampling by impulses, uniform array of impulses. And I will choose omega s to be equal to twice of omega 0. It could be more than that, but for the best efficiency, let's push it all the way down to the minimum omega s. The minimum omega s is 2 omega 0. We have this, as we know. And this is omega 0. Omega s is 2 omega 0, as we have set. And therefore, we will have a repetition like this. And then another repetition like this. It's all going exactly like this. Although I'm leaving some gaps between these triangles, sawtooth-shaped triangles, actually there's no gap. I'm just putting that gap to show that the right-hand side and the left-hand side are different things. One of them is the replica of the other one, just to indicate that I'm putting a slight gap in between. Actually, there's no gap on the frequency axis. And this is how we sample H. After sampling, when we convert to discrete time, then we come up with the discrete time, really sampled version of our system, H of n, in other words. And its Fourier transform will be H of e to the j omega, which is the magnitude of the Fourier transform of H of n. Okay, this is what I'm drawing. And we know that it's the same shape. The only difference is that omega s now will correspond to 2 pi. So I draw the same thing. This time I'm not going to indicate the gaps, because as I said, actually there was no gap. And this place will be 2 pi. This place will be pi. And the magnitude will look like that. It is periodic with 2 pi because we know that h of e to the j omega is periodic with 2 pi. So let's make it periodic with 2 pi. It was already periodic with omega s previously by sampling or by multiplying with an impulse train. Its spectrum became periodic with omega s. We make it periodic with 2 pi by assigning this way. So when I ask you the question, what is the frequency response of the discrete time filter? So this is our question. I give you this input-output relation, all right? And I want you to implement it using discrete time filters. X of t is band limited to omega 0. So the input is band limited to omega 0. What is the frequency response of the discrete time filter H in discrete time? What's the frequency response in discrete time? And the answer that you must give me must be this. This is the frequency response of the filter. The magnitude of the frequency response, of course, it's not having the phase. For those of you who are curious about the phase, it actually looks like this. So the angle of h of e to the j omega is like this. For the upgoing right-hand sided place, the phase of j omega is the phase of j that is due to j, which is 90 degrees, that is pi over 2. Like this. It's too light, I'm sorry about that. I hope you can see that. It's flat at pi over 2. And for the negative part, the absolute value must be multiplied by minus j, and that corresponds to minus pi over 2 angle. Like this, up to this minus pi. So this is pi, this is minus pi. Between minus pi and pi, these two will be the phase, and then they will repeat themselves. It's gonna go on like this. Okay, this is the angle spectrum, not the magnitude spectrum, but the angle. The magnitude is the red one, the angle is the green one. If it's more towards making a filter, of course, the magnitude is more important than angle, because it describes whether it is low pass or high pass or band pass and things like that. Do you have any idea? Can you give a name to this filter? It is something pass filter. What is that something that you put here for this derivative operator? Is it a low pass filter, a band pass filter, a high pass filter? Do you have any suggestions? High pass filter, exactly. Why is it high pass filter? Because it is passing pi. Mm-hmm. And it's not passing the DC 0. Pi is the highest frequency that you have. And it's the same as 3 pi and 5 pi. All the odd multiples of pi will correspond to the highest frequency that you can have. So it is actually, yes, a high pass filter. All right. Now, if I give you in an examination, let's talk a little bit about how can we come up with questions. If I think of asking a question, what kind of a question may I ask from here? I can give you a shape of a continuous time filter. This shape could be given to you as a shape, or it can be like this question, it can be extracted from a time domain information, from the differential equation or from the impulse response. You can somehow come up with h of j omega, okay? And that may be a low pass, it may be a high pass, etc. filter of some sort. What are you going to do with it? You will first crop that h of j omega between minus omega 0 and plus omega 0. You will have to crop it and then repeat it as if you have sampled at 2 omega 0. You repeat it, so you come up with these red shapes here. And that repetition period you make to be 2 pi and say that whatever it is, I did not write what is h of n here, but this is the Fourier transform of it. This is the frequency response. This is h of e to the j omega. So how do you find h of n then? For instance, if you have this thing, it looks like shit actually, these two things, okay? You have these two, and from these two, it means you have h of e to the j omega. But what is h of n? At that point, you have to leave it as h of n is the inverse discrete time Fourier transform of this h of e to the j omega. If you have h of e to the j omega, it means technically you are finished, because you can always, technically at least, take the inverse Fourier transform and obtain h of n. Can you find it? I don't know, maybe it just depends on whether you will be able to solve the integral of the inverse Fourier transform, or maybe you can use some properties. Okay, it's like the derivative of something, or the derivative of this one may look like something, but be careful about the j's, etc. It's a little bit tricky. It's a different question. It's like the application of inverse discrete time Fourier transform by itself, but that's not the point here. So such questions will end whenever you find capital H of e to the j omega. If you have it, if you have these two shapes, then you are finished. It means you can invert this to find h of n. And that's how you will implement or you will apply a discrete time processing of continuous time signals. So did you learn it? I hope you understood how to cut h of j omega between minus omega 0 and omega 0, and then repeat it, and then make it the discrete time system that you will apply in the computer. All right, that's how we do it. Okay, this essentially concludes the topic of sampling, but we have a few minutes before giving a break for some time, and then continue with the Laplace transform, and that is the digital to analog conversion. So let me talk a little bit about this. It's not related to asking questions or anything, but the knowledge of this is something useful. If you have a discrete time signal like this on the n-axis, so this is 0, 1, 2, 3, 4, etc. And this is x of n. You first have to convert these integer indexes to the sampling period. So, and you have to put or insert impulses. Let's assume that the capital T is this much. So This is at capital T. Of course, capital T shouldn't be more than 1. It has to be something like 0.001 seconds in terms of milliseconds or microseconds, etc. Because the frequency content should be like that. But nevertheless, I will just try to make an illustration here. So you first convert the discrete samples to impulses with the correct sampling period. Maybe like this. It's continuing like that. From here to here is the first step that you do. And then you apply a low pass filter. You remember that? What was the frequency of the low pass filter that you do? You have to apply the low pass filter at omega s over 2. Okay, that is the cutoff frequency of the low pass filter that you must apply. So this is your low pass filter, h of j omega, that you must apply. An ideal low pass filter with cutoff frequency of omega s over 2, from minus omega s over 2 to omega s over 2, all ones. This is the low pass filter that you have to apply. Now, an interesting, fascinating thing happens in the time domain when you apply this low pass filter in the frequency domain. What is the inverse Fourier transform of this? So this is on the frequency axis. What is h of t? The inverse Fourier transform of a rectangular shape. It's a sink. Thanks, Doka. And that's what we have. We have a sink. And a sink is actually extending to from minus infinity to plus infinity in time. Since it is not causal, it gives us an immediate impression that it's not implementable. You cannot do that in technical terms. So as engineers, as mathematicians, you can say that I apply an ideal low pass filter. It's there. But if you want to really implement it in real time, since it's not causal, it's not realizable. So you cannot really do it. You have to do something else. But if you could do it, then in time domain, something very nice would happen. I will draw it in orange color. It will be the side lobes of the h of t will be from minus t to plus t, first of all. That's because the bandwidth is omega s over 2. So from the formula, this will come, and the peak will be equal to 1. Sorry for writing all these in orange, but I hope you can see them, okay? When you convolve with the impulse response, when you convolve this signal, the signal is consisting of impulses, and these are the impulse responses. So you have to repeat these sink shapes at the positions of the impulses that you have for the left-hand side impulsed shape. So let's move these sinks to the positions of the impulses. For example, if you move it to the first, this first impulse, then the sink will look like this. And it's a lovely shape. Okay, that is the sink. Since this, the magnitude, the peak part of the sink is 1, when you convolve it with this impulse with some magnitude, let's say A, then the peak will be moving to A, to exactly the point of the end of the impulse, the magnitude of the impulse. So the peak will be A. If you convolve with the second impulse with that, it will be scaled according to the magnitude of that impulse, let's say B. So the sink will be like this. If you convolve with the third, it will be like this. And with the next one, it will be like this, etc. Let me draw a few. Now, when you focus to these sink shapes, or when you combine these sink shapes, okay, after the convolution, of course, we will have all these sinks, and the result is a combination of those sink shapes. When you combine those sinks, it will be the ideal continuous time signal, which is just following these peaks like this in a continuous manner. So, but how does it happen? I can at least show you that at the positions of the impulses, a sink shape which starts with the peak corresponding to the impulse location, that value will be the only contribution according to these infinitely many sinks. All the other sinks will make a zero crossing. Look at what's happening around 2t here. At 2t, all the others, at this point, all the others are making a zero crossing. So the value at 2t is only determined by this peak value of the sink. The other sinks will not contribute. They will make zero crossings, so nothing over there. So the impulse positions will be precisely equal to these values. But what is happening in between? It is just the ideal interpolation, also known as the sink interpolation. And it is the best interpolation that you can have according to the Nyquist theory. So ideal low-pass filter will make ideal interpolation, which is the sink interpolation, which acts like this. But as I say, in engineering terms, you cannot really do that. It's impossible because sink is extending from minus infinity to infinity. It's not causal. It's not even partially causal, because with some finite amount of buffer, if you can just push the frequency, the impulse response to the right-hand side a little bit, you can still implement it. The digital to analog conversion will be just delayed by half the period of the sampling or something like that, which is fine. But you cannot shift a sink signal to the right-hand side and make it still causal, because it is from minus infinity. So you have to push it all the way for plus infinity seconds. And that's not possible. But this is possible, for example. If you have an impulse here, another impulse here, another impulse here, another impulse here, you can just convolve them with this triangular shape. You can convolve them with a rectangular box. It will be a zero order hold, okay? So the digital to analog conversion will be stair. If you convolve with this triangular shape, like this, with the peak being 1, then the convolution output will be, I will again draw them in orange. It will be like this, and then like this. I'm drawing separate convolution outputs. Every time I convolve with an impulse, I make a replica. It will be like this, okay? The convolutions. And when we add up these convolutions, clearly, this line plus this line will give you this line. Furthermore, this line plus this line will give you this line. So it's just linear interpolation. It's drawing lines from the peaks of these impulses. This linear interpolation is a good enough, I would say, interpolation for digital to analog conversion. But it really doesn't correspond to an ideal low-pass filtering. It corresponds to something else. What does it correspond to? It corresponds to the Fourier transform. This is h of t. What is the Fourier transform of that? That is h of j omega. What's the Fourier transform of a triangular shape? Let me wait a little bit so that the figure arrives. Okay, we have h of j omega. What is h of j omega in other words? H of t's Fourier transform. That h of t is the linear interpolation. How does its Fourier transform look like? Will it be a rectangular box, ideal thing? No, of course not. But it will be something else. And that something else you can find by thinking that h of t, this triangle, is obtained by convolving two rectangles. If you convolve two equal width rectangles, so a rectangular box, you convolve it with itself, you will have a triangle shape. Remember convolution. Never forget convolution. Always visualize the convolution in your mind. If you convolve a rectangle with itself, it will be a triangle up and down. So h of t is rectangle convolution with a rectangle. So what is its Fourier transform? The Fourier transform is the Fourier transform of rectangle times the Fourier transform of rectangle. So because if you convolve in time domain, you multiply in frequency domain. Fourier transform of rectangle times Fourier transform of rectangle. What is Fourier transform of rectangle? It is sinc. So we will have sinc times sinc, which is sinc square. And the sinc square is some shape like this. It decays faster than sinc. Sinc was sine x over x. Sinc square is the square of it. Sine stays between -1 and 1, so its square is between 0 and 1. But x in the denominator becomes x squared, so the decaying factor will be squared. So the denominator will be omega squared. So that's why it decays faster. It's not really a perfect low-pass filter, but it's a good low-pass filter. So by convolving a rectangle with itself, I obtain a triangle and its Fourier transform is sinc square. Why don't I convolve it 3 times? So let's think of an h of t, which is a rectangle convolution with a rectangle convolution with a rectangle. Let me convolve 3 times. Then h of j omega will be sinc cube, which will converge even faster. It's even a better low-pass filter. A rectangle is a rectangle shape. Rectangle, convolution rectangle is a triangle shape, which is called, so rectangle is this shape, and its corresponding digital to analog conversion will be notated as 0 order hold, and rectangle convolution with a rectangle is like this, and it is linear interpolation. It makes linear interpolation, and rectangle convolution rectangle convolution rectangle will make a smoother shape, and it's the corresponding interpolation for that is a spline interpolation. or to be precise, this is a cubic spline interpolation. The others, by the way, the zero order hold and linear interpolation are also spline interpolations. They are not cubic, they are lower grade spline interpolations. So the more you convolve with a rectangle, you come up with higher order splines, and the interpolations will be smoother and smoother. The first one, the zero order hold, was not smooth at all. It's not even continuous. The linear interpolation makes it continuous, but not differentiable, because the joints will be like this, sharp joints. And if you apply a cubic spline, it will be differentiable. And from there on, it will proceed to be better, getting better and better. This kind of a spline interpolation can be used. You choose one of these usually for digital to analog conversion, because these are finite. These impulse responses are finite. Therefore, you can push them to the right-hand side by some finite amount using memory buffers, and it will be implementable, realizable. Although none of them are causal. They are not causal because there are some parts at the left-hand side in the time domain, but you can just push them to the right-hand side to mimic some causal behavior. So this is how the digital to analog conversion literally works. We don't really apply a sync interpolation. The sync interpolation is the ideal case, and it's not realizable. So we interpolate using these usually. So these are the things that I would like to talk about in the topic of sampling, within the topic of sampling. Now we will give a 15 minutes break. So it's, let's start at 10:12. Okay. At this hour, we will meet again at the same place. So right now I'm stopping the recording.